Last time we were writing the equation of exponentials and we expanded our basic equation of y equals a times b to the x. We expanded that to be y equals a times 1 plus or minus r to the x power. Today we're going to go ahead and expand it again. That's called compound interest. So we're going to look at this formula right here. So instead of just having the 1 plus r in our parentheses here, we have 1 plus r over n raised to the nt power. So first let's talk about what all these variables stand for. This final value here is our total amount. The P here is in the place of the initial amount. We said initial amount fell right there. That's still it. It stands for principal when we're talking about compound interest because that's what they call the initial amount in money. So this is principal. Which is the initial amount. R is the rate. And remember, that's a percentage turned into a decimal. T is time, so none of those have changed. And N is the number of times compounded. That part's really important because you're only going to use this formula when it says it's being compounded. Other than that, we would go back and revert to our basic equation, y equals a times b to the x, or our y equals a times 1 plus or minus r to the t power. But if it says that we are going to compound it, then you must use this formula. And the number of times you compound is going to be that n value. It says when any 4 are known, the fifth can be found. And so the values of n, that number of times compounded, depends on how much they tell you it's going to compound. If they say it's going to compound monthly, well, that happens 12 times in a year, so the n value would be 12. Semi-annually is twice a year, so that's going to be 2. Annually only happens once. Quarterly happens 4. Daily happens 365. So those are the most common ones that we're going to use. So when it says compounded monthly, then you know that the n value is 12, and that's where you would plug those two in there. So we're going to look at some examples of this. And we do have all 3 equations written here. We're going to get to this compounded continuously a little bit later. But we have all 3 formulas written for you here. Here is the very basic one. Last class, we extended that to a times 1 plus or minus r to the t power. Today, we're going to expand it to the compound growth, and then we're going to get to where it compounds continuously. We will only use this compounded continuously when it says compounded continuously. This equation is basically like our first one here. The P is principal, which is the initial amount. E is a number. It's kind of like pi is for geometry. E is like that for algebra 2. So E is 2.718281828, and it keeps going just like pi does. Now, your calculator will give you that number just like it does for pi. Right above the caret symbol, you see the pi symbol used in geometry. Right above the division, you will see that E symbol right there. That's our E. If we hit second division, it will give you the E there. And then if you hit enter, you'll see that 2.718281828. Now, when you want to do yourself a favor and remember that E is approximately 2.72, just like pi is 3.14. Now, it does go on forever, so when we calculate it, we're going to use the E in the calculator to make sure they use all the decimals. R is the rate, and T is the time. And again, you will only use that when it says continuously compounded. Otherwise, we're going down to our other equations here. All right, so we'll look at some examples. It says you deposit $3,500 in an account that pays 5% annual interest, compounded continuously. What is the balance after 5 years? So we see this compounded continuously. And so we know we're going to use this equation here. Most of the time, you'll hear us call that PERT. So we're going to start with that A equals P times E to the RT. All right, when we're compounding, that means that we're going to stop at some point, figure out how much interest, and we're going to add that to the pot. and then it's going to move forward again. We'll stop again and add our interest to it. So you're making interest on interest. Compounded continuously just means we're going to stop all of the time and add that interest. All right. 3,500 is our initial amount, so that would go in the place of the P. E again is a number, not a variable, so that will stay the same. Our percentage here is 5%, so we would want to put 0.05 because we want to move that decimal over 2 places. So our rate would be 0.05, and then our years are 5. That's how long we're going to leave that in that account. Now that we filled in the information that we know, we can go ahead and figure out how much money we're going to have at the end of those 5 years. So we get 3,500. We're going to do that E, and there's actually a second E, just so you know. To the left of the 4 right here, there's an E that already raises it to the power. Because that's the way we use it most of the time, it's with that exponent. Then they've done that second key right above the natural log button right there. So we'd hit second and then that button, and that's going to give me E and raise it to a power. If not, you can do the other E with the caret symbol. Our rate is 0.05, and we are multiplying that times 5 years. And so we've got 4494.09. Remember, with money, you want to leave 2 decimals. So the amount of money that we have after 5 years is 4,494.09. The way they can make this question a little bit trickier is by asking you how much interest they made. This is how much money we started with. This is how much money we have after 5 years. So the difference between those two is how much money you made in interest. All right, number 2, $3,500 is deposited in an account that pays 5% annual interest, compounded annually. Find the balance after 5 years. The more you compound, the more money you're going to make. In this case, they're only compounding annually. So they're going to stop once a year, figure out how much interest you've made, and add that to your total amount. And then the next year, you would pay that interest on interest. So we're going to use our compounded formula here. And we get 3,500 is still the initial amount. When we're using this one, since it's annually, the n is going to go away since it's 1, but we'll go ahead and put it in so you can see what that looks like. That's 0.05 over 1 times 1 times 5. Since these are 1, it goes to the simple interest one, which is the one that we did last time here, where it's just got the 1 plus or minus r. We'll go ahead and put this in our calculator now, and you can put it exactly the way you see it. So we hit 3,500, 1 plus. If you do the alpha y equals, that allows you to put it in as a fraction. 0.05 over 1 raised to the 1 times 5. So I put it exactly the way it is on paper so it doesn't mess up any order of operations, and it gives us our value, 4466.98. So you see you made a little bit less by compounding less. All right, we're going to do the same thing now and just show you on different values. So for quarterly, we said that would be 4 times our n. Monthly, that would be 12. And daily, that would be 365. So I'll do a couple of these just so you can see. I'll start with this monthly one here. We've got 3,500, 1 plus 0.05 over 12 raised to the 12 times 5. Quick little shortcut on the calculator here. If you're doing these with the same setup, you can go ahead and use the arrow key and highlight that and then hit enter, and it will do the setup for you, copies and paste it. That way all I'm doing is changing the 12 here. And so now I've got 4491.76. There's a couple examples. So you see the more you compound, then the more it's going to accrue. So this was going to be the one with the most because that's compounded continuously. Then it goes to the compound monthly. and then it goes to that annually. If we did daily, it would be somewhere in between this one and this one here. So the more you compound, the more you are going to make. Now we're going to look at another type of exponential, a half-life equation. It tells us a patient had to take 50 milligrams of iodine 131 to treat his thyroid disease. Iodine 131 has a half-life of 8 hours. Half-life is the amount it takes a substance to decay to half of its original amount. So that's what a half-life problem is. It is the amount of time it takes a substance to decay to half of its original amount. All right, so in this case here, our original amount is 50. So that is going to be our A value. What is the growth or decay rate? The only thing we know is that half. So that's what we're going to put in the place of B. And this would be that just basic equation, y equals b to the x power. So we want to write our equation here. Now when I write this and I get 50 times 1/2, and I want to put the time here. If I just leave time the way it is there, then every single hour it is going to half it. Because this t is our exponent for the 1/2, it's going to multiply times 1/2 on every single one of those units of measure, which in this case we're writing in hours since that's the information given. We don't want it to half every hour because it says it halves every 8 hours. So I need to divide this time by 8. That way it is doing it every 1/8 of an hour so that it does the full thing after 8 hours and gives us our entire half. So we are dividing by 8 here. Because it does not divide it doesn't half every hour. All right, how much was left in his body after 1 day? Since this equation was in hours, because our initial information was in hours, we need to convert that there to hours. So we're going to convert that to 24. And when we write our equation, we get y is equal to 50 times 1/2 to the 24 over 8. Now we can type that into the calculator and we get approximately 6.25 milligrams. All right, when did the amount drop below 1 milligram? So he wants to know when he needs to take it again, so we need to figure out when it's below the 1 milligram. In this case, they're giving us our total amount, so we would want to plug that in for the y. The initial amount stays the same, the decay factor stays the same, and our time portion stays the same. Now, since we won't learn how to solve these until we get to logs, the only way you can do this is with the calculator at this point. And so we're going to go ahead and plug this into y1 and this into y2 to find the intersection where it is that amount. So we get 50 times 0.5 raised to the x divided by 8. Oh, sorry, you've got a glare there. There we go. And then we're going to put the 1 in the y2. I'm going to make my window so that I can see this. And so 50 is probably going to be too much, so I'll lower that. And then y max, definitely 50,000 is way too much. So we started with 50, so anything above 50 is going to work. So I'll do 75. I hit graph here. All right. You want to be able to see the intersection so you can get that. In this case, I did go too small. I want to be able to see the intersection, so I need to open it further to the right. So I'm going to open my window up here so that the x max is bigger. So let me just go back to that 50. And so now we can see the intersection there, so our calculator is able to give us that. So we hit second trace intersect, enter, 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 and there it is at 45.15. Time is continuous, So we do want to leave a decimal for that. So approximately 45.15 hours is the iodine going to be in his body to be more than 1 milligram. All right, we're going to go a little bit further with that. In here, it tells us in half-life situations, the half-life is rarely 1. So again, you're going to have to really work with that time part of it. It says, for example, technetium-99 is a radioactive substance used to diagnose brain, thyroid, liver, and kidney diseases. The half-life of it is 6 hours. If the half-life is 6 hours, how many times does technetium-99 have in 12 hours, and in 6 hours, and in 1 hour? So the first thing you want to think about, if it is happening every 6 hours, then we know that at 12 hours, it should be happening 2 times. At 6 hours, it would happen 1 time. And at 1 hour, it would happen 1/6 of a time. That's the reason why it's important to get that time portion in the exponent correct. So if we were to write the equation on this one, where we started with 200 milligrams, our total amount would be equal to 200 milligrams, half-life, and then it's not every hour, it's every 6th hour. So we would put that in there as T over 6. Now, if we plugged in 1 for the time, just like it was here at 1 hour, it'd be the 1/6. If we plugged in 6 hours here, 6 divided by 6 would be 1 and give me the 1 time. If we plugged in 12 here, 12 divided by 6 would give me a 2 up here, which is exactly what we were looking for, 2 times. That's where that division part is coming from, and it's really important that you're able to set that up. This last type of equation that we're going to look at here is one where an equation is given for you. Some of the equations with exponentials are difficult. They're going to give you the formula in there, and then you just want to make sure that you know how to use it. In all cases, our initial amount occurs right at the front here. We're going to have some kind of growth factor and some kind of time up on the top. So here it tells us tritium is a radioactive substance used to eliminate exit signs. The amount of tritium disappears over time, a process called radioactive decay. The number A of milligrams left after 2 years is given by this equation. That means that's the formula we want to use, where A naught is the initial amount. If you start with 10 milligrams of tritium, how many milligrams are left after 10 years? So our total amount is still going to be out at the outside part. Our initial amount is still at the beginning here, so we're going to have 10. They told us the growth factor is E, so we use E. And then it gives us this rate here. And then for our time, we would plug in 10. So just like the other ones, if they give you a formula, just use the formula in the problem to solve the problem. We plug this into the calculator using the E from the calculator. And so we get our total amount left is 5.69 milligrams. Any equation where they give you it, that means that that's the formula they want you to use. All right, for our last type of problem here, and this is a more challenging type of problem where you really have to think through the exponential that's going on here. It says, Kate has found some radioactive material in the school courtyard. To protect the school, she stores the 80 milligram substance in a lead container. After 3 days, only 1.25 milligrams remains. What is the half-life of the mysterious substance Kate named catonium? All right, so it's asking what is the half-life? Remember, the definition of a half-life was the amount of time it takes a substance to decay to half of its original amount. So that's what we want to find, is the time that it took to get to half of its original amount. At this point, we don't know what that time is. So we can set up, we do know that after 3 days, there's 1.25 milligrams. So our total amount left was 1.25. So I'm going to put that in for the amount. Our initial amount was 80. So I can plug that in for our initial amount. We're looking for that half of its original amount. And we know it's been 3 days. And so we are looking for 3 days out of what is going to give me that to give me my H value? How many hours that's going to give me? All right. So we're going to go ahead and plug this in the calculator. However, we haven't learned how to find the exponent yet. We need a log to solve that, so we'll do that later. Right now, we're going to take this and we're going to plug one side into y1 and the other into y2 to find the intersection. All right, when we plug that in and find our intersection, we find that the h is 1/2. So that intersection occurred at 1/2, 1.25. So our h is 1/2. Since we put this in days here, we know that means half of a day. So it has a half-life of half a day. That means that it happens twice a day. Half the day goes by and it goes down to half of its initial amount. Another half of the day goes and you're back to another half. So it is happening twice a day. So if we wrote this equation then for the half-life, our total amount would be equal to 80 times 1/2, which is the growth factor, and twice a day would be 2 times our t value. Because the half-life is half a day, it is happening twice in a day. So our equation would be multiplied 2 times each day there. And then to find when it's below 0.1, again, we would put 0.1 on the amount. And we would solve for this t by taking this and plugging it into y1 and y2. We find the intersection, and our time would be approximately 4.82 days. So that's some more of the formulas that we have for exponentials. At this point, you should be familiar with when to use and where to use these equations. This is the very basic one. So when they're giving you the growth factor and an initial amount, this would be where you start. If they're giving you a percentage of increase or decrease, then that's where you use the next form. 1 plus if it's growing, 1 minus if it is decreasing. If it tells you compounding and it gives you a specific amount of time, then that's where you're going to use this compound interest. And n would be that number of times that it tells you. So compounded monthly, compounded daily, it has to tell you a specific amount of time. If it says compounded continuously, then you are going to use our PERT equation. So it's really important that you read what is going on and which one you want to use. Once you've determined that formula, then it's just plugging in the points and using the calculator to find it. When we're talking about half-life problems, you are talking about the basic one, and that growth factor would be 1/2. So get comfortable with knowing the equations and using them.